Hi, in this video I am going to do complete revision on cosmology, mainly focused on Edexcel IAL Unit 5 syllabus. Uh, Normally when we start this topic, students ask what is the importance of studying cosmology, or some students they ask what are the real world applications of cosmology. Okay, so there are no such real world applications, but all the study or complete study related to cosmology depends on the light we receive from the star or star cluster or galaxy. The light that we receive from these stars or star clusters or galaxies are older light. The light from sun takes almost 8 minutes to reach us. That means the light that you see now was emitted 8 minutes ago. Like that, the nearest star to Earth other than the sun is the Alpha Centauri. The light from the Alpha Centauri takes almost 4.35 years to reach us. So the light that you see now, which was emitted from the Alpha Centauri, was emitted almost 4.35 years ago. By using very powerful telescopes, scientists are able to receive light, or they are able to see light from several billion light years away from us. Light year means the light that travels during 1 year. The distance the light travels during 1 year is called light year. So if scientists can see stars several billion light years away, means that light was emitted billions of years ago. So by using the spectrum of these lights, scientists are able to analyze what happened several billions years ago, how physics principles involved in the creation of universe, how physics principles evolved or changed during several billions years ago. Also, scientists can analyze how energy, matter interacted during those periods, that is several billions years ago. Or that actually the universe is actually it's a natural laboratory for scientists to test certain experiments. That means like a very critical situations, like very high temperature, very high pressure, how these physics principles behave during these situations. So normally in the laboratory we won't be able to create such very high temperature, very high pressure, but naturally it exists during the Big Bang or even after the Big Bang. Also, scientists can predict what could happen in future, what could be the fate of the universe. So like this, cosmology actually something related to research. In that way, it's an important study, because all the physics principles were created after the Big Bang. So scientists are interested about how the physics principles are changing during several billions years ago, or how the physics principles could change in future. There are researches going on like that. Okay, so in your syllabus, that is Unit 5 syllabus, we mainly focus on certain measurements. That means how to measure the temperature of a star, how to measure the luminosity of a star, or how to measure the distance of different stars, galaxies, and how the lifespan of a star changes. Those are the things we are going to learn, because actually we are not going to learn the real cosmology. To learn the real actual cosmology, you should have very good knowledge in thermodynamics, special theory of relativity, general theory of relativity, then about electromagnetic wave theory. Everything you should have good knowledge in those things. But in Unit 5 syllabus, you don't need to worry much. It's actually we are using only 3 laws and Doppler. The 3 laws means we are using Stefan Boltzmann law, Wien's law. Those 2 laws, nothing related to cosmology. They are actually related to the Stefan Boltzmann law and Wien's law. Both are related to black body radiation, nothing related to cosmology. Same way, Doppler effect. or Doppler shift. That also nothing related to cosmology. That is related to waves, how the wavelength and frequency changes when an observer and the source has relative motion. So only one law we are learning related to cosmology, that is Hubble's law. Other than that, we are trying to do certain measurements in Unit 5 syllabus by using the physics principles or the laws. They are related to some other physics principles like wave theory or something like black body radiation. Okay, so there's nothing to worry about cosmology. The questions are the calculations related to cosmology also based on only these equations. Additionally, there could be calculations related to intensity I equal L over 4 pi d squared. So that you already studied in Unit 2. Okay, so the first law that we learn in this topic in Unit 5 under cosmology is Stefan-Boltzmann law. I already told that Stefan-Boltzmann law nothing related to cosmology. That is related to black body radiation. So what is black body? Black body means it's a physical object or a physical system or an object that absorbs all the radiation, electromagnetic radiation falling on it, and it emits radiation depending on its temperature. So black body should be a perfect absorber. It should absorb all the electromagnetic radiation falling on it, and it emits radiation in a wider range, with a wider range of wavelength. And the distribution of the radiation should be governed by the temperature. So that is the black body, right? So the Stefan-Boltzmann law relates the luminosity, how the luminosity of the radiation emitted by a black body depends on certain properties of the black body. So luminosity means power of the radiation is called luminosity. So luminosity is denoted by L. So luminosity, the Stefan-Boltzmann law says that luminosity is directly proportional to the surface temperature of the surface area of the black body. Also, it's directly proportional to the power 4 of the absolute temperature of the black body. So when we combine these two things, it will become the luminosity is directly proportional to A t to the power 4. So when we convert this to an equation, L equal sigma A t to the power 4, where sigma is called Stefan-Boltzmann constant. It has a value, the sigma value is equal to, that's given in the data sheet, 5.67 into 10 to the power minus 8 watts per meter squared Kelvin to the power minus 4. That's the value of Stefan-Boltzmann constant. So this is the first equation. So there were calculations based on this equation. So sigma, we know that, so that's given in the data sheet. So other than that, there are three other quantities. Luminosity, that's the power of the radiation emitted by the black body. A is the surface area, T is the temperature. So out of these three quantities, they'll give any two and they can ask the fourth one. Those are the questions comes in the past papers related to calculation. Okay, so the next law is the Wien's law. Wien's law is also related to black body radiation. So I told that black body means it should be an object or system that absorbs all the electromagnetic radiation falling on it. Okay, then it should emit radiation, electromagnetic radiation with a range of wavelength, and that wavelength should depends on the temperature. The emitted wavelength should be related to the temperature. So the Wien's law tells that the luminosity of, it's actually a curve, that's an equation is there, but there's a graph. I'm going to show that. That graph shows that how the luminosity of the emitted radiation depends on the wavelength. So for example, at a particular temperature, if I draw a graph for luminosity against wavelength of the emitted radiation. So at a particular temperature, the distribution will be something like this. So that means at a temperature T1, the wavelength emitted by the black body, the electromagnetic radiation emitted by the black body will have a range of wavelength. All those wavelengths won't have the same luminosity. Different wavelengths will have different luminosity. So this particular wavelength will have this particular luminosity. This wavelength will have some other luminosity. So like that, the luminosity will be different for different wavelengths. Also, it says that when the temperature decreases, if you have another black body that has lower temperature, what happens? The wavelength that correspond to the peak luminosity will increase. So in this particular temperature T1, there is a wavelength lambda 1 that gives the maximum luminosity at this temperature. But when the temperature decreases, the distribution curve will become like this. The distribution curve will become like this. So there, at this temperature T2, the black body is at a temperature T2. At this temperature, there is a peak luminosity. The wavelength that gives the peak luminosity is lambda 2. So if I consider another temperature T3, which is lower than T2, so there the distribution will be like this. The wavelength lambda 3 gives the highest luminosity at temperature T3. So like that, it's a distribution curve. Wien's law tells about how the luminosity varies with different wavelengths of the emitted radiation. So the Wien's law says that lambda 1 times T1, where lambda 1 is the wavelength that correspond to the highest luminosity at temperature T1. So here temperature T1 greater than temperature T2, temperature T3. So T3 is the lowest temperature, T1 is the highest temperature. When the temperature is the highest, the luminosity, the peak value of the luminosity will be higher, and you can see the wavelength that correspond to the peak luminosity will become smaller, highest temperature. So the temperature decreases, the peak luminosity will decrease, and the wavelength that correspond to the peak luminosity will increase. So he found a relationship between the wavelength that correspond to the peak luminosity and the temperature of the black body. So he showed that lambda 1 T1 is equal to lambda 2 T2, that is equal to lambda 3 T3. So he found a constant that is 2.898 10 to the power minus 3 meter. Unit of lambda is meter, unit of temperature is Kelvin, so meter Kelvin. So this is called, this numerical value is called Wien's constant. Okay, so generally we write this equation like this. So where lambda 1, lambda 2, lambda 3, they all correspond or related to, or they are correspond to the wavelength which gives the highest luminosity at that particular temperature. So we write that lambda max. So lambda max does not mean maximum wavelength. The wavelength that correspond to the peak luminosity times the temperature of the black body is equal to constant, which is 2.898 10 to the power minus 3 meter Kelvin. So this is the Wien's law. This relationship is the Wien's law. So the two laws we learned just now, Wien's law and Stefan Boltzmann law, both are related to black body radiation. So can we use this for in cosmology? Yes, we can use, because you know even sun is a star and any other stars, they behave as almost black bodies. So you know the sun absorbs radiation, not only sun, even other stars, they absorb radiation. So you can ask me, what is the experimental evidence to show that star or sun absorbs radiation. Okay, if you focus telescope to the sun and receive the spectrum, you know it's a very hot object, so it should give continuous spectrum. Hot objects give continuous spectrum. That means all the colors should be there from violet to red. But there are absorption lines in the emission spectrum of the sun, or even from any other stars. When you see the spectrum, there will be absorption lines. So those absorption lines depends on the type of gas in the star. So that means that shows sun and other stars are absorbing certain radiation, but they are not absorbing all the radiation, but they are absorbing certain wavelength of radiations. So stars, including sun, are not perfect black bodies. So they show certain behavior closer to black body. So they are emitting radiation. Their radiation emitted from the stars depend on the temperature. So in that way, they are not perfect black bodies, but they show certain, up to certain extent, they show the behavior of black body. So that's the reason we use Stefan Boltzmann law and Wien's law for the stars in cosmology. Okay, so simple calculations related to these two laws. The first one, surface temperature of alpha set is about 3600 Kelvin. Calculate the wavelength at which the intensity of radiation is maximum. So to find it, we should use the Wien's law, the first part, A part. So I can say lambda max into T equal to 0.898 10 to the power minus 3 meter Kelvin. So I need to find the lambda max is going to be 2.898 10 to the power minus 3 divided by the temperature, which is 3600 Kelvin. So the peak wavelength will be equal to, or wavelength that correspond to the peak luminosity, that will be equal to 8.05 10 to the power minus 7 meter. Okay, B part, calculate the power emitted per unit area from alpha set. So that means, you know, power means luminosity, L equal sigma A T to the power 4, but the question is calculated power emitted per unit area. So L over A, luminosity per area, is sigma T to the power 4. So we know the sigma, Stefan Boltzmann constant, that is 5.67 10 to the power minus 8 times the temperature 3600. So 3600 to the power 4. So this much of watts per meter square. Watts per meter square. So solve it, you will get the answer that will be equal to 9.52 10 to the power 6 watts per meter squared. Okay, so how can we measure the surface temperature of a star by using these laws what we learned? Okay, so it's simple. You must know this. They can ask in the exam. They earlier asked also. So how can we measure the surface temperature of a star? Okay, you know, we assume stars behave as black bodies. So what we do, we use a powerful telescope to receive the light or radiation emitted from the stars. So it's better to use a satellite telescope. Satellite telescope means a telescope which is fixed on a satellite, because if you try to receive radiation from Earth, the radiation from the stars, certain wavelengths could be absorbed or scattered by the atmosphere. So we might lose that radiation in our experiment. So to avoid this unwanted loss, we can use a satellite outside the Earth's atmosphere, which is fixed on a satellite. So by using a satellite telescope, receive the radiation from the star. You are going to measure the temperature of that particular star. So receive the radiation from the star. Disperse the radiation into different wavelengths. In your syllabus, you know that by using diffraction grating, you can split the white light or split the radiation into different wavelengths, something like that. Disperse the radiation received from the star into different wavelengths. Measure the intensity of each and every radiation after it is dispersed. You can use a light meter or something like that. There are sensors are there. You can measure the intensity of each and every wavelength of the radiation that we receive from the star after that radiation is split into or dispersed into different wavelengths. Measure the intensity of each and every wavelength. Okay, identify the most intense wavelength. So most intense radiation first. So you know, when you are measuring the intensity of each and every wavelength, identify which radiation is giving the highest intensity. So that's the most luminous radiation. Then we should find the wavelength of that particular radiation. How can we find? In your syllabus we can say by using double slit experiment. Simple. There are a lot of methods. There are Newton's rings. So there are many methods, but in your syllabus unit 2 we learn how to measure the wavelength. So by using double slit. So by using a method, find the wavelength of this particular most intense radiation. So you know the wavelength, that is the lambda max. That is the lambda max, because you are measuring the wavelength of the most intense radiation. So that is going to be the lambda max. You know the lambda max. Use the Wien's law. Lambda max into T equal 2.89 at 10 to the power minus 3. From that, find the T, that is the surface temperature of the star. Okay, so by using Wien's law, we can find the surface temperature of a star. Okay, I'll repeat it again. Focus a satellite telescope to the star, receive the radiation from the star, disperse it into different wavelengths, and identify the most intense radiation after dispersion. Measure the wavelength of this most intense radiation, that is lambda max. By using Wien's law, lambda max into T equal 2.89 at 10 to the power minus 3, find the T, that is the surface temperature of the star. Okay, so the next thing you should know, the main sequence star and star classes. So what is meant by main sequence star? You know, all the stars including sun emit radiation or emit heat and energy due to nuclear fusion reaction. So in all stars nuclear fusion is happening. So main sequence means, or main sequence star means, if there is a significant amount of hydrogen fusion happens or occurs in the core of the star. Core means the central part of the star. So when there is significant amount of hydrogen fusion occurs in the core of the star, then that star is called main sequence star. You know, when you think about the after the Big Bang, you know, initially plasma were created, then fundamental particles were created after certain amount of years. Later, hydrogen nuclei were created. So the hydrogen nuclei or hydrogen atoms, they attracted each other due to the gravitational force, and when they hit each other, hydrogen fusion started. So that is the protostar. When I tell you the lifespan of the star, I'll tell you again. But that's the way the stars are formed due to hydrogen fusion. So main sequence star means a star that has significant amount of hydrogen fusion in its core. The word core is important. In its core is called main sequence star. Okay, so when a star is in main sequence, so you know the meaning of main sequence, where significant amount of hydrogen fusion occurs in the core of the star. When a star is in the main sequence, the star experiences two different types of pressure, we can say. The first is due to inward gravitational pressure. The first pressure is called inward gravitational pressure because you know a star consists of huge, tremendous amount of gas, mainly the hydrogen in its core. So there will be very large gravitational force acting on all the gas particles that causes very large amount of inward gravitational force, and force per unit area is the pressure. So that is called inward gravitational pressure. So due to this inward gravitational pressure, the star should shrink and burst, but that never happens when the star is in the main sequence, because due to hydrogen fusion, the star is emitting radiation in the form of photons. You know, photons carry momentum. I told that in unit 4. Momentum of a photon is given by P equal E over C, where P is the momentum of the photon, E is the energy of the photon, C is the speed of light. So due to the momentum carried by the photons, they exert force on other gas particles in outward direction. That is called outward radiational pressure. So when a star is in the main sequence state, it experiences two different type of pressures. One is the inward gravitational pressure and the other one is outward radiational pressure. So when the star is in the main sequence, these two pressures balance each other, so the star will have a stable state in its main sequence. Okay, so depending on the mass of the star, the temperature of the star varies. Say for example, if the star has very large amount of mass, say for example we compare it with the mass of the sun, which is called solar mass. If the mass of the star is much greater than 4 times the solar mass, what happens? It will have very large inward gravitational pressure. So due to that, core will have very large density. The hydrogen molecules or hydrogen atoms inside the core will be compressed a lot due to the inward gravitational pressure, which given by a huge amount of mass. So what happens? The density will increase. You know that to sustain or continue the hydrogen fusion, the collision among the hydrogen particle or hydrogen molecules should be at very high rate. So due to the very high density, the rate of fusion will be very high. So for massive stars, the rate of hydrogen fusion will be very high. Why? The reason is much larger inward gravitational pressure will cause the density of the core to be very high, so the rate of fusion will increase. When the rate of fusion increases, what happens? The temperature of the massive star will be much larger. When the temperature is much larger, according to Wien's law, lambda max T equal constant, when you consider that way, 2.898 10 to the power minus 3, when we consider this equation, so these massive stars have much larger temperature, so the wavelength lambda max, the wavelength that corresponds to the peak luminosity, will be much smaller. So you know, in the visible spectrum, the lowest wavelength is almost blue or violet. So massive stars will appear bluish. Massive stars will appear bluish. The reason, again I'll tell you, massive stars have much larger mass that causes very high significant amount of inward gravitational pressure that causes very high density. Rate of collision among the hydrogen fused particles will increase, that causes high rate of fusion. Due to high rate of fusion, what happens? The temperature will be very high. So due to the high temperature, lambda max becomes very small. The wavelength that corresponds to the peak luminosity will become very small. That is in the visible spectrum closer to blue color. So massive stars appear bluish. Same way, low mass stars. So if the mass of the star is much smaller than 4 times the solar mass, what happens? The density of those stars, even when they are in the main sequence, the density of those stars will be much lower. So density lower means rate of collision will be lower. So rate of collision lower means rate of fusion will be lower. Rate of fusion lower means temperature will be lower. So temperature lower means lambda max, the wavelength that corresponds to the peak luminosity, will be larger. In the visible spectrum, the highest wavelength corresponds to red color. So these low mass stars appear reddish. There will be other stars in the range between blue and red. There will be different color stars there. You know, sun looks little bit yellowish. Yeah, so it's somewhere in the between. Okay, so depending on the mass of the star, all the stars exist are classified into 7 classes. So the 7 classes are, you don't need to remember that. So these are the 7 classes: O class, B, A class, F class, G class, K class and M class. These are the 7 classes. O class stars are the massive stars. These are low mass stars. So as I explained, massive stars appear bluish. You must be able to explain why those stars appear bluish. You know that large inward gravitational pressure that caused by the huge amount of mass. The rate of collision increases because density will be much higher. Rate of collision increases means rate of fusion is higher. So the temperature will be higher. So according to Wien's law, it becomes blue color because lambda max will be lower. I already explained that. So the massive stars appear blue color. Low mass stars, they also main sequence stars. M class stars are low mass stars. They appear red color. Low temperature, high temperature. So other stars fall in between O and M class stars. Okay, next thing is about mass of a star and lifetime in main sequence. Okay, we know that O class stars are massive. Their mass is very high. It consists of huge amount of hydrogen in its core. But O class stars are, sorry, I made a mistake. O class stars are massive and they consist of huge amount of hydrogen in their core. But M class stars are low mass stars. They have less amount of hydrogen in the core. So which of these two stars, I'll compare only the O class stars and M class stars, which of these two stars will remain in the main sequence state for longer time? You know, actually, O class stars have very high mass, but even they have very high mass, their lifetime in the main sequence is much lower compared to M class stars. The reason is due to much larger inward gravitational pressure, the rate of fusion will be very high in O class stars. Due to much higher rate of fusion, the hydrogen will be fused during shorter periods. So shorter periods means the O class stars will remain in the main sequence for several millions of years, but M class stars have lower rate of fusion. So lower rate of fusion means they will keep the hydrogen in their core for longer periods. So they will remain in main sequence for billions of years. O class stars can remain only for millions of years. So the lifetime in the form of main sequence state is much lower for O class stars. The reason, due to their massive mass, the rate of fusion is very high because of inward gravitational pressure. You know, it supports or influences the hydrogen fusion by giving sufficient amount of density. So the hydrogen will be used up in a shorter period. So they can be in the main sequence, M class, O class stars. They can be in the main sequence only for few millions of years. But M class stars can be in the main sequence or several millions or billions of years. Okay, so next topic about stellar evolution. Stellar evolution means how the star changes during its lifetime. Okay, so we classify this into 2 groups. Normally the stellar evolution is classified into 2 different types. One is called lifespan of low mass star, the other one is called lifespan of massive star. As I told earlier, stars are classified into 8 classes, but in terms of, that is depending on the color and the mass, we classify them into 8 classes. But here, depending on the stellar evolution, how the stars changes during their lifetime, depending on that, they are classified into 2 groups. They are like we call that stellar evolution of low mass star and stellar evolution of massive star. So what do you mean by low mass star? Low mass star means if the mass of a star is less than or equal to 4 times of the solar mass. Solar mass means mass of the sun. So if the mass of a star is less than or equal to 4 solar mass, then that type of star is called low mass star, and its lifespan is a particular type. Same way, if the mass of a star is more than 4 times the solar mass, that is called massive star, and its lifespan is different compared to lifespan of low mass star. So we are going to analyze these two different types of lifespans. So okay, so stellar evolution of low mass star. Low mass star means if the mass of the star is less than or equal to 4 times of the solar mass, that is called low mass star. Okay, so initial first stage is protostar. So protostar means where the hydrogen molecules have started the fusion. So that is called protostar. When it collects more and more hydrogen due to gravitational pull, and when the hydrogen fusion becomes significant in its core, then it will become main sequence star. Sometimes it's called sun-like star. So that's a main sequence star. Some books they call sun-like star. So that means where significant amount of hydrogen fusion occurs in its core. It will be in this state for several millions of years depending on the mass. Anyway, the mass is less than or equal to 4 times the solar mass. But depending on the mass, it could be in several millions years or few millions years depending on that. Okay, so what happens when it is in the main sequence star? It experiences, as I told earlier, two different pressures: outward radiational pressure due to the momentum of the photons emitted from the fusion, and the inward gravitational pressure due to the mass of the star. These two pressures will balance each other. So remember that when a star is in the main sequence, these two pressures will balance each other, so the star will stay in the main sequence without any change in its size or other properties. The temperature also will remain almost the constant. Then what happens? When the star, the core hydrogen fusion occurs, when the hydrogen is fused, the outcome or the product will be helium. So gradually the hydrogen molecules in its core will decrease, and when the hydrogen is exhausted, what happens? The core will be mainly occupied by helium. There could be a little bit of hydrogen in the outer layer of the core, but core will be occupied by helium when the hydrogen is exhausted. So there is no much further outward radiational pressure inside the core, so the core will shrink. When the core shrinks, what happens? The temperature of the core will increase and the rate of fusion becomes less. So since the rate of fusion becomes less, the temperature of the star will decrease. So that means in this state, the star is leaving the main sequence. So until hydrogen occupies in the core and the significant fusion in the core is hydrogen, the star will be in the main sequence. So when the hydrogen is exhausted, core will be occupied by helium. There could be certain amount of hydrogen in the outer layer or next layer of the core, but inside the core there won't be any hydrogen fusion, and helium fusion not yet started. So what happens? There is no outward radiational pressure, so the core will shrink due to the inward gravitational pressure, and due to the less amount of radiation, the temperature of the star will decrease. When the temperature of the star decreases, and the core will shrink. When the core shrinks, whenever a gas is compressed like that, when the core shrinks, again the temperature will increase, and that temperature will fuse the hydrogen gas in the outer layer of the core. Due to this hydrogen fusion happening in the outer layer, what happens? There will be outward radiational pressure from the outer layer, which is outside the core, due to that fusion, hydrogen fusion, outward radiational pressure will be emitted. That will make the outer layer to expand and the star will become giant. That is called red giant. Okay, so when the star becomes red giant, what happens? The amount of increase in surface area will be very large. Therefore, according to Stefan Boltzmann law, L equals sigma A T to the power 4, the temperature will decrease. I told that the hydrogen fusion inside the core is not much enough. So the star, there could be little bit of hydrogen fusion in the outer layer. When the core shrinks, it emits radiation, it emits temperature. That temperature will be used, or heat will be used to fuse the hydrogen in the outer layer. Because of that hydrogen fusion in the outer layer, there will be outward radiational pressure that will cause the outer layer of the star to expand. So the star will become much larger. The increase in surface area is very high. Very large amount of increase happens in the surface area. Because of that, luminosity will increase. Temperature is decreasing. Surface area is increasing. Temperature decreasing. Surface area increasing. Luminosity also will increase. Since the temperature is decreasing, according to Wien's law, a constant that is 2.898 10 to the power minus 3, according to Wien's law, what happens? The lambda max will increase because T is decreasing. The star will become more reddish. The star will become red color. We call it as red giant. So after the main sequence state, the star will become red giant. So when that happens, red giant state occurs when the core is occupied by helium, and inside the core there is no hydrogen fusion, so core is shrinking, but there could be little bit of hydrogen fusion in the outer layer. When the core shrinks, temperature of the core will increase and heat will be radiated. That heat will fuse hydrogen in the outer layer, and there will be outward radiational pressure from the outer layer of hydrogen in the outer layer. That will cause the outer layer to expand. That's the reason the surface area of the star becomes much larger. So when the surface area becomes larger, luminosity becomes much higher. The temperature I told already decreasing. So if the temperature decreases, lambda max increases, star will become red and very big. That is called red giant. Okay, so it could be in millions of years in the state of red giant. Now what happens? Now inside the core, I told that core is shrinking. The heat produced, the temperature increases, heat produced. That heat will be able to fuse the helium. So when the helium fusion becomes significant inside the core, the outward radiation pressure will become very large and the outer layer of the core will be thrown away into the space, and that will cause planetary nebula. So when the helium fusion becomes significant in the core, the amount of energy radiated due to helium fusion is very high. Outward radiational pressure becomes very large, and that throws away the outer layer of the star. So the outer layer will be thrown away into the space, and that will form planetary nebula. So after that, only the core will remain. Now when the core remains after throwing the outer layer, the core has not enough mass to continue the fusion. So the fusion inside the core will be sustained. No further fusion. So there is no outward radiational pressure from the core when it comes to the planetary nebula state. No outward radiational pressure. The core will shrink due to much larger inward gravitational pressure. So when it shrinks, what happens? The temperature will increase and it will become white color. So it will become white color, much smaller due to inward gravitational pressure. So that is called white dwarf. Okay, so when the star becomes white dwarf, that is the final state, but it will emit radiation due to the temperature to the surrounding, so no further fusion reaction. Due to the temperature, it appears like a fainted white color, but gradually when it loses heat to the surrounding, the intensity of that white color can decrease, and later the white dwarf will become brown dwarf, and finally it will become black dwarf. So theoretical model says the time required to become black dwarf is more than the current age of the universe. So there are no black dwarfs in the universe. Okay, again, so quickly we'll compare. This is the initial stage of the star where the hydrogen fusion is starting. When it accumulates more and more hydrogen nucleus, the mass will increase and there will be significant hydrogen fusion in its core. That is the main sequence. It could be in the main sequence for several millions of years. Depending on the mass, it could slightly, it will vary. Okay, so then the red giant star occurs. What's the difference between red giant star and main sequence star? So when a star is in the main sequence, significant amount of hydrogen fusion occurs in its core. Outward radiational pressure will be balanced by inward gravitational pressure. So when it is in the main sequence, the state will remain same, the property of the star will remain unchanged, its luminosity, temperature, all will remain unchanged. But when we consider several millions of years, there could be slight difference, variations, but generally we can say when a star is in the main sequence, its properties remains unchanged. So when the hydrogen is exhausted, you know, when hydrogen is fused, helium will be produced. When the hydrogen is exhausted, core will be occupied by helium. There could be little amount of hydrogen in the outer layer of the core. There could be little bit of hydrogen fusion occurs in the outer layer. So in case that time, what happens? The core will shrink because the core has no fusion, no outward radiational pressure, but it has large amount of inward gravitational pressure, so the core will shrink due to inward gravitational pressure. When it shrinks, when a gas is compressed, what happens? Pressure increases, that will cause the temperature to increase. So temperature of the core will increase. When the temperature of the core increases, it will radiate heat, and that heat will support the hydrogen fusion in the outer layer of the core. So there will be hydrogen fusion in the outer layer of the core. So that hydrogen fusion in the outer layer will give out outward radiational pressure and exert force on the outer layer of the gases. Then what happens? The outer layer will expand. When the outer layer expands, it becomes giant, huge surface area. But the temperature is lower because there is no significant amount of hydrogen fusion and helium fusion not yet started. So it will become red giant. So when it becomes red giants, what happens? The luminosity will be higher because surface area is higher, temperature becomes less. So according to Wien's law, lambda max will become larger, it becomes reddish. So it will be leaving the main sequence. But when it becomes red giant state, perfectly red giant state, what happens? Inside the core, there will be helium fusion because the core will continuously shrink and the temperature increases, and that will support the helium fusion. But when the helium fusion becomes significant, the outward radiational pressure becomes much more because the energy released during helium fusion is much more compared to hydrogen fusion. So when the core is occupied mainly by helium and when the helium fusion becomes significant, the outward radiational pressure will become much more compared to inward gravitational pressure. So what happens? Due to the large outward radiational pressure, the outer layer of the star will be thrown away into space, and that will form planetary nebula. After planetary nebula is formed, the total mass of the star is decreased because outer layer has thrown out. So the mass of the core is not sufficient to produce further fusion of helium. Helium fuses will produce carbon, so there will be carbon also. It can't fuse the carbon because temperature is not enough. So what happens? There is no further fusion in the core, but there is inward gravitational pressure. The star will shrink. Whenever gas shrinks, temperature will increase. so it will become white color. That white color is due to the temperature only, not due to fusion. It's due to the temperature. It becomes white color. It emits almost several radiations. So due to that radiation, it will become fainted white color. That will become white dwarf. So the temperature, when you compare the temperature of the white dwarf is more than temperature when it is in the main sequence. Could have be. You can see the chart diagram later. So temperature of the white dwarf is normally more than temperature of the main sequence star. Luminosity of the white dwarf is much lower compared to main sequence star because the faint light will be emitted. That light is only due to the temperature. So temperature of the white dwarf will be more than temperature of the same star when it was in the main sequence, but the luminosity will be much lower compared to when it was in the main sequence. When you compare red giant and white dwarf, the surface area much larger, much smaller surface area, much higher luminosity, much lower luminosity, much lower temperature, much higher temperature. They can ask what's the similarity between main sequence star and red giant. Similarity, you can say both have hydrogen fusion, but difference. Hydrogen fusion occurs in the core, hydrogen fusion occurs in the outer layer. Careful, the difference means, similarity means both have hydrogen fusion. Yeah, but where that hydrogen fusion occurs is the difference. Here the hydrogen fusion occurs in the core, here hydrogen fusion occurs in the outer layer. Right? So those are the similarities and differences between main sequence and red giant. Okay, so next thing is about stellar evolution of massive star. That also, you know, massive star means if the mass of the star is more than 4 times the solar mass. You know what's the specialty there? The inward gravitational pressure will be much higher. So the rate of fusion will be much higher, right? So here also the initial state is the protostar. So when it gets more and more hydrogen nuclei, it will become main sequence star. So the main sequence star is called blue supergiant. It's called blue supergiant because massive and much larger. So it's called blue supergiant. So that is the main sequence star. So in this state here also, inside the nucleus, there will be a significant amount of hydrogen fusion occurs. But when the hydrogen fusion is completely used up or exhaust, helium will be occupied, the star will leave the main sequence. So as I explained in the low mass star, when it leaves the main sequence, it will become red giant. Same explanation. So red giant means, here we call, some books they call red supergiant, or some books they call red giant. Okay, but here the difference is the star has very high mass. So it could be in the red supergiant state inside the core until iron is formed. You know, when hydrogen is fused, it will become helium. When helium is fused, it will become carbon. Like that, when carbon is fused, you don't need to remember like all the outcomes of fusion. The finally iron will be formed. Until iron is formed, the red supergiant can withstand even very high amount of outward radiational pressure. It can withstand because it has very large inward gravitational pressure. But when you compare the red giant of low mass star, it was unable to withstand for the outward radiational pressure given by significant amount of helium fusion from the core. It was unable to withstand, so that's the reason it threw away the outer layer and formed planetary nebula. I'm talking about the low mass star. But in massive star, the star could be or will be in this state of red supergiant state until iron is formed, because its inward gravitational pressure is very high and it can withstand to very large outward radiational pressure given by different types of fusion reaction. When iron is formed, what happens? You know, in the radioactivity you would have learned when you think about binding energy per nucleon against mass number graph. When you think about the binding energy per nucleon, against nucleon number or mass number, the graph is something like this, and it goes like this. So the highest binding energy per nucleon occurs for iron. So that means you know the binding energy per nucleon indicates the stability. That means when iron is formed, you can't fuse iron further, because if you are fusing the iron, the product will be on the right side. You know, during fusion, the nucleon number increases for the product. So if the iron is fused, the product will have larger nucleon number, but it has lower binding energy per nucleon. Lower binding energy per nucleon means its stability is lower. So that means iron cannot be fused inside the core of red supergiant. So when iron is formed inside the core of the red supergiant, there won't be any further fusion reaction, because iron cannot be fused there at that particular temperature. It's not possible because outcome is unstable, so energy will not be released. You would have learned that in radioactivity. So if the outcome or the product becomes stable only, energy will be released. So to have a fusion reaction in which the product is unstable means you need to supply energy to have such fusion. So here energy is not released, because the product, if you fuse the iron, the product will have low binding energy per nucleon, it's unstable, so the fusion will not happen and energy will not be released. So if there is no further energy released, what happens? The outward radiational pressure won't be there, or will become significantly lower, but inward gravitational pressure is huge. So due to inward gravitational pressure, the core will shrink heavily and suddenly. When the core shrinks, pressure increase and there will be explosion. That explosion is called type 2 supernova. So here the explosion happens due to sudden shrink or compression in the core. That causes the explosion. But in planetary nebula form, when the outward radiational pressure throw away, in low mass star, throw away the outer layer. Here, no further fusion, no outward radiational pressure. So the star, the core will shrink due to inward gravitational pressure, and when it shrinks, the pressure becomes very high and the core will explode, and that is called type 2 supernova. So after the explosion, the most of the mass will be thrown out. So the core remnant will become or could become two different stages after the explosion. So the next stage I can say is red supergiant will become type 2 supernova. During type 2 supernova, yes, iron can be fused because the energy released during that explosion is very high. That energy can fuse even iron, not only iron, beyond iron also the fusion will happen. They are saying that's the way other elements in the periodic table are created during supernova. Okay, so the type 2 supernova will be there. After the red supergiant, there will be explosion called type 2 supernova. Then after the supernova, the core remnant could become two different types. If the mass of the core remnant is lower than 3 times of the solar mass, it will become neutron star. So if the mass of the core remnant after type 2 supernova is less than 3 times of the solar mass, it will become neutron star. It consists of full of neutrons. If the mass of the core remnant after the type 2 supernova is more than 3 times of the solar mass, it will become black hole. So black hole means it has huge amount of inward gravitational pressure, it will shrink a lot and the density will become very high. It can attract even light. That is the black hole stage. Okay, so next topic is Hertzsprung Russel diagram or HR diagram. So it's actually a plot. Y-axis indicates relative luminosity. Relative luminosity means luminosity of a star or star cluster relative to luminosity of the sun. So L over L naught. L naught is the luminosity of the sun. X-axis is the temperature in Kelvin. So here the temperature, the x-axis is marked in a different way. Normally in graphs, we start from lower to higher, but here it's marked with higher to lower. It starts with 40,000 or 60,000. With equal ratio it's marked, not equal intervals, equal ratio. So careful. So it's 40,000 Kelvin, then 20,000. Difference is 20,000. Here 10,000. Then 5,000 and 2,500, or you can start with 60,000, 30,000, 15,000, 7,500, like that. You can, with the same ratio, mostly the ratio is taken as half. Y-axis is the relative luminosity. So relative luminosity of the sun is 1. Luminosity of the sun divided by luminosity of the sun is 1. Okay, the main sequence I already explained, that is marked along the diagonal in this way from left top to bottom right. So these stars or these plots indicates the main sequence stars. So these are the main sequence stars. So it should be little up. Sorry. They won't ask to draw. They never asked like that. But you should be able to mark the positions of different things, like, so sun is somewhere here, so this could be 1. Sun temperature is almost 5,600, 5,800 Kelvin. Okay, so this is 1, this is 10 to the power 2, 10 to the power 4, so here 10 to the power minus 2, 10 to the power minus 4. Here also, that those are given with the ratio. Right, so you can see where to mark the main sequence. I already marked it. So where to mark the white dwarfs? I told white dwarfs temperature will be higher than when it was in the main sequence. So if you think about our sun, when the sun becomes white dwarf, the temperature will be more. The temperature of the sun is somewhere here 5,600. So it will be more when it becomes white dwarf. We can mark the white dwarfs up to around 18-20,000. So these are the white dwarfs. Their luminosity is lower, much lower compared to luminosity of sun. So the luminosity will be 10 to the power minus 2 or 10 to the power minus 4 order. These are the white dwarfs, this stage. Okay, red giant, we have to mark. Red giants have higher luminosity but lower temperature. So they'll be towards right, somewhere here. Red giants will be in this position. So little more further towards right, more than 5,000. So somewhere here. Super red giants could be somewhere here. So these are the red giant states. So this is the white dwarf, red giants, main sequence. You should be able to mark them on a HR diagram. That you should know that. Okay, so next thing about measurement of distance of a star or galaxy. That's very important here in your syllabus. So different units are used when we talk about distances of different galaxies and stars from us. Us means from Earth. We don't give it in kilometers. So there are 3 different units we introduce in your syllabus. First is called astronomical unit. The first unit is called astronomical unit. So it's denoted by AU. So kilometer denoted by km, like that it's denoted by capital A, capital U. So what it means, astronomical unit, how do we define astronomical unit? So it's defined as the average distance of the Earth from the Sun is defined as 1 astronomical unit. So 1 astronomical unit has a value in kilometers, that's average distance of the Earth around the Sun, that is 1.5 into 10 to the power 11 meters. That is called 1 astronomical unit. So you can find 2 astronomical unit, 1.5 astronomical unit, anything you can find. If you want, you can convert to meter. Okay, the second unit we use in your syllabus to measure the astronomical distances. Astronomical distances means whatever the distance measured in astronomy, right? So second unit we use is light years. So what is light year? Denoted by Ly. So what is light year? I already told that the distance light travels during 1 year is called light year. So during 1 second, the light will travel 3 into 10 to the power 8 meters during 1 second. So 1 light year is the distance traveled by the light during 1 year. So 1 light year means the distance the light travels during 1 year. So during 1 second, it will travel 3 into 10 to the power 8. During 1 minute into 60, during 1 hour, during 1 day, during 1 year, 365 meters. So solve it, you will get the amount, the magnitude of 1 light year. So that will be equal to 9.46 10 to the power 15 meters. Okay, so the third unit what we use in your syllabus is called parallax second. The third unit in your syllabus we called parallax second. Denoted by PC, symbol P, symbol C. Shortly it's called parsec. Parallax second, shortly it's called parsec. The notation for parallax second is PC, Lightyear, Ly, Astronomical Unit AU. I defined the meaning of astronomical unit and Lightyear. So how do we define parallax second? Okay, I'll define it now. Okay, so before defining parallax second, you should know that 1 degree in protractor, but it's not marked, but 1 degree could be divided into equal 60 divisions, and each division is called 1 minute. So that means 1 degree is equal to 60 minutes. 1 minute means 1 over 60 degree. Same way, 1 minute is divided into equal 60 divisions, and each division is called second. So that is 60 second. So that means 1 second is equal to 1 second is equal to 1 over 60 minutes. That means 1 degree is equal to 3600 second. 1 degree is equal to 3600 second. This is the notation for second. This is the notation for minute. Okay, so you must know this, right? So how do we define? So 1 second means 1 over 3600 degree. 1 second means 1 over 3600 degree. Okay, so how do we define 1 parallax second? Okay, so we define parallax second like this. We know that Earth is orbiting the Sun. So this is the Sun. Earth is orbiting the Sun. So how do we define 1 PC or 1 parallax second means? Now if we could find a point in space, if we could find a point P in space such that the angle Earth, this is the Earth, the point P Sun, this angle, we should be able to imagine this. We can find a point like that, but we imagine like this. There could be a point P in space such that the angle Earth, point P, Sun becomes 1 second. If that happens, distance of that point P from the Sun is called 1 PC. I hope you understood. How do we define? In space, we imagine a point P such that the distance, sorry, the angle Earth, point P, Sun becomes 1 second. If we find a point P such that the angle becomes 1 second, then the distance of the point P from the Sun is defined as 1 parallax second. So by using this definition, we can get a numerical value for 1 parallax second. So we know that average distance of the Earth from the Sun is 1 astronomical unit, 1 AU. I already defined it. And we know how much is 1 AU in terms of meters. So here you can say tan 1 second in this right angle triangle. In this right angle triangle, tan 1 second is equal to opposite, that is 1 AU over this distance. So this distance is going to be 1 PC. I'll call it as D over D. So D is going to be 1 AU over tan 1 second. So you know that 1 second is equal to 1 over 3600 degree, and we know 1 AU in meters, that is 1.5 10 to the power 11 meter divided by tan 1 second, means tan 1 over 3600 degree. Solve it. When you solve, you will get 3.09. So here you will get, I write it here, D is equal to 3.09 into 10 to the power 16 meter. That's the distance D. That makes this angle 1 second, which is 3.09 10 to the power 16 meter. This distance is defined as 1 parsec. This is defined as 1 PC. So that means 1 PC equal 3.09 10 to the power 16 meters. Okay, so next topic is measuring the distance of a star or galaxy. That is one of the important topic in your syllabus. Okay, so different methods are used with different accuracies. Say for example, there's a method, first we are going to learn, called Trigonometric Parallax method. That method is suitable to do measurements up to a star at a distance of 100 parsec or 100 parallax second. You can't use that method if the distance of a star is more than 100 parallax second. So I'll let you know after explaining the first method. We call it as trigonometric parallax second. So it has, actually it's a much better method compared to other methods I'm going to tell, but it has good accuracy, but its limitation is shorter. You can measure or you can use that method, which is called trigonometric parallax method, only up to a distance of 100 parallax second. So I will explain that method now. Okay, so normally we say this method called trigonometric parallax method is used to measure the distance of nearby stars. Nearby stars means up to a distance of 100 parallax second. Okay, you know that the method how we use, here this is the sun. Earth is orbiting the sun almost a circular path. So we are going to measure the distance of a nearby star. So this is the star, its distance we are going to measure. Okay, so when we are taking measurements, mainly here we are going to measure the angle. So when we are measuring an angle, we need a reference point. Okay, so how do we take the reference point? You know, normally you would have noted when you walk and when you see a far distance object, or maybe when you in the night when you see moon and when you walk you feel the moon is coming with you. So the thing is, when the distance becomes much larger, the change in position, your change in position won't affect the position of the far distance object. So here what we do in this method, we need a reference line to measure the angle. We take light from far distance stars. Say for example, there could be a star much far away somewhere here. The light from far distance star, when the Earth is here, we observe that star. Maybe the Earth is here. When the Earth is here, we see the star, light from a far distant star somewhere here. So light from this star when we see that light will be taken as the reference line when we are taking the measurements of angles. So what the method, first I'll tell the method. What we do, when the earth is here, we measure the position, we focus the telescope to the star and we take a particular measurement. Then after 6 months, the earth will be exactly in opposite side here. There also, we take the measurement for the nearby star by using the same star, the light from the same star. So for example, if the light from the star which is much far away, when it reaches Earth, whether here or here, it looks like parallel. So if you draw a line from here to that part, something like this, maybe this, I'll take this, I couldn't draw here. If I take this as the far distant star, somewhere here, and this is the far distant star, same star. Okay, now when I erase this part, you see that these lines appear almost parallel. So light from far distant star appears almost the same alignment even when the position of the earth changes. So we use that light from far distant star as a reference light, and we measure the arc difference. So we take a measurement when the earth is here. After 6 months we take another measurement relative to the light from the far distant star. So we measure this angle. We measure this angle alpha 1, could be alpha 2. So this angle will be alpha 1 plus alpha 2. That is called change in angular displacement or arc difference of the nearby star during 6 months period. So we can measure this angle alpha 1 plus alpha 2. Alpha 1 is this one, alpha 2 is this one. So this angle will be alpha 1 plus alpha 2, because these two red color lines indicates the light ray from far distant star. The light from the far distant star is taken as a reference line. So related to that line, we measure these two angles. So the angle Earth, star Earth during 6 months period, this is called arc difference or angular displacement of the star during 6 months. So if I know this angle, we measured this angle during 6 months, alpha 1 plus alpha 2. I know this distance, this is 1 astronomical unit, 1 AU. So now I can use trigonometry to find the distance of the star from the Earth by using, we don't need to do any calculations. So we can find the distance of the star from Earth during 6 months, or even distance of the star from Sun. There is no big difference because these angles are very small, less than 1 degree normally. So we can measure the distance of the star by using trigonometry. Okay, so if the symbol diagram I can draw, the Sun is here, Earth is orbiting like this. So imagine symbol diagram, Earth is here, exactly here, the star is exactly here, but that won't happen always. If the star is here, I can measure this angle. So this angle we can measure, symmetrical nature. So this angle will be bisected, this line will be bisected. So if I know this angle, this will be half of it. This line, 1 astronomical unit. So simply I can say tan theta, this angle if I say theta, this also theta, symmetrical, yeah. Tan theta equal 1 astronomical unit over this length. I can find the distance of the star from the Sun, or I can use sin theta, which is 1 astronomical unit over this distance. So if the diagram is a symmetrical, but that won't happen always when we are doing practical. So the line what we draw from the star to the Sun and the line drawn from Sun to the Earth won't make 90 degree always. Okay, so here it won't make 90 degree. So we need to use the trigonometry, we can find it, but that type of calculations you won't get it. If you are getting a calculation, it will be in this format. This angle will be 90 degree. You can use tan theta or sin theta for this triangle. Okay, so normally they ask to describe the method that is called trigonometric parallax method. They normally ask to explain. So this is the 4 points, they give 4 marks. First you should say measure by using the light from far distance star as a reference line. Take measurements during 6 months interval. By using these measurements, find the angular displacement or arc difference of the nearby star. Second mark. We should know the distance of the Earth from the Sun, which is 1 astronomical unit. Third mark. By using trigonometry, find the distance of the star from the Earth. Those are the 4 marks they gave. Last, I think it appeared 3 times in the past paper. That is the marks given for that. Again, I am telling, measure during 6 months interval by using light from far distance star as a reference line. Measure the angular displacement or arc difference of the nearby star. 1 mark. You should know the radius of the Earth's orbit around the Sun. We should measure by using trigonometry. We can measure the distance of the star from the Earth. These are the 4 points they gave in the past paper. Okay, so what is the limitation of this method? Why can't we measure a star which is at a distance more than 100 parsec? Say if the distance of a star is more than 100 parsec, if the star is somewhere here, what will happen? The angle, this angular displacement or arc difference will become smaller. You can draw a simple diagram and see, difficult to draw it on the board, but if you draw, you can see that this angle will become smaller. Compared to this angle, this is smaller. So when the angle becomes smaller, we won't be able to measure that angle by using any apparatus. Maybe it could become smaller than the precision of the apparatus. So the percentage uncertainty will become larger. So that's the reason this method has limitation. But this method is a good method for nearby stars. But this method has limitations. We can use this method only up to a distance of 100 parsec. Okay, so if the distance of a star is more than 100 parsec, we can't use trigonometric parallax method. So the next method is spectroscopic parallax method. So spectroscopic parallax means here the spectrum is used. Actually, we as I explained earlier, how to measure the temperature. Here, what we do, we focus the telescope, receive the radiation from the star, and disperse its spectrum into different wavelengths. Identify the most intense spectrum and find its wavelength. By using Hertzsprung Russel diagram, we should assume that the star is in the main sequence. That's one of the drawback in this method. We assume the star is in the main sequence. So by you assuming the star is in the main sequence, use the Hertzsprung Russel diagram to find the luminosity of this star. After finding the luminosity of the star, we know the luminosity, measure the intensity of the light from the star. So we know the intensity of the star, we know the luminosity by using I equal L over 4 pi d square. We had these equations in unit 2 also. The intensity varies inverse square law. So what we do, again I am telling, focus the telescope to the star, receive the radiation, identify its spectrum, disperse into different wavelengths, identify the most intense radiation in the spectrum and find its wavelength. After finding the wavelength, use Wien's law and find the temperature that correspond to the wavelength with highest luminosity. Then use the Hertzsprung Russel diagram. So in the Hertzsprung Russel diagram, this is the temperature, this is the relative luminosity. So this is the main sequence star. So we assume the star is in the main sequence. It's a wrong assumption, but there's no other option. We assume the star is in the main sequence. So if the temperature is something like this value, from the HR diagram, find the relative luminosity. Since we know the luminosity of the sun, we can find the luminosity of the star. Now we know the luminosity of the star. Then measure the intensity or radiation flux for the light coming from the star. Measure the intensity. We know the luminosity, we found it. By using I equal L over 4 pi d squared, find the distance. Okay, so here in this method, the drawback or the limitation is we assume the star is in the main sequence. That's one of the biggest mistake. We don't know whether it's in the main sequence, but we assume the star is in the main sequence. But when you go through different books or other internets, they tell this method in a slightly different way by using apparent magnitude, actual magnitude. But in your syllabus, we don't use those those words or those techniques, apparent magnitudes, absolute magnitude. So your syllabus, we use this way, that is measure the see the radiation from the star, find its spectrum, disperse it into different wavelengths, identify the most intense radiation, and the relevant wavelength should be measured. By using Wien's law, measure the temperature of the star, surface temperature of the star. Use the HR diagram, assume the star is in the main sequence. By using the temperature, what we found, find the relative luminosity of the star. Since we know the luminosity of the sun, we can find the luminosity of the star. Also measure the radiation flux or the intensity of the radiation from the star. We know the I, we know the L, so find the D by using this equation. This method also has limitation. This method can be used up to a distance of 10,000 parsec. So if the distance becomes more than 10,000 parsec, what's the problem occurs? The problem is there will be difficulty in identifying the most intense radiation. You know that when the distance increases, the intensity of the radiation. So here we are focusing the telescope and we are dispersing it. After dispersing it, we are measuring the intensity of each and every wavelength after dispersion, and we are identifying the most intense wavelength. So we might be able to measure the intensity of the radiations, but the variation might occur beyond the least count of the measuring instrument. So if that happens, we won't be able to identify the most intense radiation. There will be measurements, you might get numerical value for the intensity of each and every radiation after dispersed, but you won't be able to identify the most intense radiation because they all might appear the same. There will be difficulty in identifying the most intense radiation when the distance of the star becomes more than 10,000 parsec. So when the distance becomes this method, more than 10,000 parsec, we can't use spectroscopic parallax method. We need to go for the next method. There we use standard candle. That means standard candle means a star with known luminosity. There are two different methods. We can use Cepheid variable as a standard candle, or we assume the luminosity of a star is known. Either way we can do. I'll explain that in my next method. Okay, next topic is standard candle. What do you mean by standard candle? Means a star or an astronomical object with known luminosity. Several times they asked in the past paper, what is standard candle means? A star or an astronomical object with known luminosity is called standard candle. Okay, we can use standard candle in three different ways to find the distance of a galaxy or star. The first one, it's like this. We should be able to measure the distance of a nearby star by using a trigonometric parallax method. So we should be able to measure the distance of nearby star by using trigonometric parallax method. So we know the distance. We should be able to measure the intensity or radiation flux of the radiation from that star. So we will be able to measure the intensity or the radiation flux of it. We are able to measure the distance of that star by using trigonometric parallax. So by using I equal L over 4 pi d squared, we will be able to measure the luminosity of that nearby star. Okay, we can find the luminosity without any problem. Then we need to measure the distance of a far distant star. Okay, there what we use we assume the luminosity of this far distant star is same as the luminosity of nearby star, or we assume both stars are similar stars. By taking that assumption, we use this luminosity for what we measured for the nearby star. That luminosity is same for the far distant star because we assume both stars are similar stars. It's an assumption, so it might go wrong if this assumption is wrong. We assume the luminosity of far distant star is same as the luminosity of nearby star. So we know the luminosity of the far distant star. We measure the radiation flux of the star. We know the I. So by using 4 pi d square, we measure the d. Okay, so here this is the standard candle because we know the luminosity of far distant star. How do we know? We measure the luminosity of a nearby star. This star and far distant star are similar stars. So we don't know the luminosity of far distant star initially. So we measure the luminosity of nearby star. How do we measure? We know the distance. We can measure the distance of nearby star by using trigonometric parallax. D we measured, I we measured, L we calculated for the nearby star. Then we assume the far distant star and the nearby star are similar stars. Our aim is to find the distance of far distant star. So we know the luminosities are similar. We measure the intensity. We know the luminosities are similar. So I and L are known. We find the D. But this way, when we are using standard candle method in this type of measurements, we make an assumption, that is the far distant star and nearby star, we consider two different stars, they are similar. We assume that their luminosities are same. We assume that. If that assumption is wrong, then the measurement what we do in distance will go wrong. So this is not a good method, but this method also introduced in your syllabus. They are using this method also in your syllabus. We take it as a standard candle one method. The second method is we use Cepheid variable as a standard candle. Okay, what is Cepheid variable? Okay, what is Cepheid variable? So Cepheid variable is a star in which the luminosity varies periodically because that star expands and contracts periodically due to variation in its pressure. So the surface area changes with same amount of time intervals. So the luminosity will vary like this. If you see the luminosity of the star or Cepheid variable with time, there could be variations like this. A proper time interval, there will be variation. Different Cepheid variables have different time periods. So this is the one time period. This is the time period. So for different Cepheid variables, the time period of expansion and contraction could be will be different. Okay, so there are many Cepheid variables closer to us, and we can measure their distances very accurately. So we can measure their average luminosity accurately. So there are a lot of Cepheid variables closer to us. We are able to measure their average luminosity because luminosity is varying with time. So their average luminosity and their time period of expansion and contraction accurately we can measure. Then if we plot a graph of their average luminosity against time period of expansion and contraction, the best fit line will be a straight line. The best fit line will be a straight line. Okay, so we got this information by using Cepheid variables. Those are closer to us. We are able to measure their luminosity by using trigonometric parallax method. The distance could be measured. We can measure their intensity by using I equal L over 4 pi d squared. We can measure their luminosity or average luminosity. We can measure their intensity or average intensity. Those are closer to us. We can measure their distances by using trigonometry parallax method. So we can find their average luminosity, and if we plot a graph of average luminosity against period of expansion and contraction for different Cepheid variables, the best fit line will be a straight line. We got this data by using several Cepheid variables closer to us. Right. Now we can use this information to find the distance of a galaxy. Mostly this method, the Cepheid variable as a standard candle method, is used to measure the distance of a galaxy which is far away from us. Okay, so how to measure the distance of a far away galaxy? We should search and find a Cepheid variable in that galaxy. That galaxy might have several Cepheid variables. Pick one Cepheid variable from that galaxy. Measure its period of expansion and contraction. You can see when you observe the intensity, how it varies. You will see the intensity will vary periodically. From that, you can find the period of expansion and contraction of that Cepheid variable in a far distance galaxy. You know the period of expansion and contraction. Use this graph. By using this graph, since you know the period of expansion and contraction of that Cepheid variable in a far distance galaxy, use this graph. From this graph, find its average luminosity. Now you know the average luminosity of that specific Cepheid variable in a far distance galaxy. You know the average luminosity. Measure the average radiation flux or intensity of the radiation from that specific Cepheid variable. So you know the intensity, you measured it from the Cepheid variable in a far distance galaxy. You know the average luminosity, you found it by using this graph. You know the average luminosity. By using this distance, find the distance of that particular Cepheid variable in that galaxy. Like that, in that galaxy, take the distance or measure the distance of different Cepheid variables in that galaxy and find the average distance of the galaxy. I hope you understood. Again, I'll quickly repeat again. Cepheid variable means a star that has periodic expansion and contraction due to periodic variation in its pressure. So its luminosity will vary periodically. Different stars have different period of expansion and contraction. There are many Cepheid variables closer to us. We can measure their distance by using trigonometric parallax without any problem. We can measure their average intensity or average radiation flux. Since we are able to measure their average intensity and we are able to measure their distances by using trigonometric parallax method, we are able to measure their average luminosity. There are several Cepheid variables closer to us, I told. So if we take average luminosity and the relevant period of expansion and contraction for different Cepheid variables, and if we plot a graph of average luminosity against period of expansion and contraction, the best fit line will be a straight line. We are going to use this information to find the luminosity of a far distant Cepheid variable in another galaxy. Okay, our aim is to find the distance of a far distance galaxy. So to find that distance, we should search and spot a Cepheid variable in that far distance galaxy. Okay, there could be many Cepheid variables. Take one particular Cepheid variable, find out its period of expansion and contraction. How can we find the period of expansion and contraction? Receive the radiation continuously from that Cepheid variable, and you know that intensity or radiation flux from that specific Cepheid variable have a periodic variation. From that, find the period of expansion and contraction of the Cepheid variable. Use this graph. By using this graph, you can find the average luminosity of that Cepheid variable in far distant galaxy. Okay, you know the average luminosity. You can measure the average intensity of the radiation from that specific Cepheid variable. So I you know, L you know. By using this equation, find the distance of that Cepheid variable in the far distance galaxy. Same way, find the distance of different Cepheid variables in the same galaxy. Find the average distance of the galaxy from Earth. Okay, so this method also has limitations using Cepheid variable as a standard candle. This method can use up to maximum distance of 50 megaparsec. Okay, so if the distance becomes more than this, the problem is identifying the or measuring the variation in the maximum and minimum intensity or maximum minimum luminosity, identifying the difference between maximum and minimum intensity or luminosity of the Cepheid variable will be difficult by using the measuring instrument. So we won't be able to find the period of the Cepheid variable. So that's a drawback or the limitation of this method. So we can measure up to a distance of 50 megaparsec using Cepheid variable as a standard candle. Okay, so if the distance of a galaxy, now we don't need to measure the distance of a particular star. We measure the distance of a galaxy now. If the distance of a galaxy is more than 50 megaparsec, we follow another method in which we use Doppler effect. Doppler effect is also nothing related to cosmology, something related to waves. Some of the syllabuses they teach Doppler effect with wave theory. Okay, what is Doppler effect? Means when there is relative motion between the source and observer, the wavelength or frequency measured by the observer will be different compared to actual wavelength or actual frequency emitted from the source. Say for example, you would have noticed that when ambulance approaches you, when the ambulance moves towards you, you are stationary, and when the ambulance approaches you, you will hear the siren with higher frequency. When the ambulance moves away from you, you will hear the siren, the sound of the siren with lower frequency. So that is due to relative motion between you and the ambulance. So I did a complete lesson on Doppler effect. I'll give you the link for that. It's a separate video. I'll give you the link for the Doppler effect. Fully, I did it complete video. In the description of this video, I'll give the link for that. Those who are interested, you can watch that. Okay, so Doppler effect, what it that? Several times they ask that. So in case if they ask what is Doppler effect means, you can say change in wavelength and frequency due to relative motion between the source and observer is called Doppler effect. So I call Doppler effect when the source is moving towards a stationary observer. The wavelength measured by the observer will be smaller than the actual wavelength emitted by the source, and the frequency measured by the observer will be higher than the actual frequency from the source. Same way, if the source moves away from a stationary observer, wavelength measured by the observer will have a larger value than the actual value, and the frequency measured by the observer will have smaller value than the actual value. So in your syllabus, we have Doppler effect equation only for electromagnetic waves. Actual Doppler effect equation related to sound is different compared to what I am going to show the equation now. So this equation is valid only for electromagnetic radiations, right? Light and electromagnetic radiation. So the Doppler effect equation in your syllabus we use is delta F over F equal delta lambda over lambda equal V over C. Okay, delta F means I told that whenever the wave source moves towards you or moves away from you, the frequency that you measure will be different compared to actual frequency. So delta F is the difference between the apparent frequency. Apparent frequency means frequency measured by the observer is called apparent frequency. So delta F is the difference between the apparent frequency and the actual frequency. Same way, delta lambda is the difference between apparent wavelength and actual wavelength. Apparent wavelength means wavelength measured by the observer is called apparent wavelength. So delta lambda means difference between the apparent wavelength and the actual wavelength. Here F is the actual wavelength emitted by the source. actual frequency emitted by the source. Lambda means actual wavelength of the wave emitted from the source, where v is the speed of the wave source relative to observer, speed of the wave source relative to observer. C is the speed of electromagnetic radiation, which is 3 into 10 to the power 8 meter per second. So this is the Doppler effect equation, only applicable for electromagnetic radiation. Okay, so you should know in your syllabus, when the wave source relatively moves away from the observer, the apparent wavelength will become larger than the actual wavelength. When the wave source moves towards the observer, apparent wavelength will become smaller than the actual wavelength. Same way in terms of frequency, when the wave source moves away from the observer, apparent frequency will become smaller than the actual frequency, and then the wave source moves towards the observer, apparent frequency will become larger than the actual frequency. So we use this method, this Doppler effect, to measure the speed of recession of the galaxies. You know, all the galaxies have almost the same type of absorption spectrum. So you know what is galaxy? Galaxy means it consists of several billions of stars. A group of stars is called galaxy. So if we focus the telescope to different galaxies, their emission spectrum should be almost the same. But there will be absorption spectrum, you know, absorption lines, due to the certain frequency of radiations absorbed by the gases in the galaxy, the gases of the stars in the galaxy. So when we observe different galaxies, those are closer to us and far away from us, they found the absorption lines are identical. Say for example, when you consider a nearby galaxy, if the absorption lines are like this, this is violet, this is red, this is nearby galaxy. If you see the absorption spectrum in a far distance galaxy, the absorption lines, these are the absorption lines, what you learned in Unit 2 under spectrum. So far distance galaxies, the absorption lines have a similar pattern. The double line will appear here, the single line will appear here, this single line will be here, this single line will be here. So the similar pattern, but the absorption lines will be shifted towards red color. This is far distance galaxy. So far distance galaxies have shift in absorption spectrum or absorption lines, means according to Doppler effect, those galaxies are moving away from us. So they are the light sources, wave sources, they are moving away from us. When you see another galaxy which is much far away from us, in which the absorption lines will be similar, but this double line will be somewhere here, this single line here, this single line here, this will be here. So it will have further shift towards red color. They are moving away from us because the wavelength is increasing towards red color. So by using the shift in the wavelength and by using the Doppler effect equation, we could be able to find the speed of recession, the speed at which those galaxies are moving away from us. So what Hubble did, for different galaxies, he measured the speed of recession of those galaxies by using Doppler effect method. Also, he measured the distances of those galaxies by using Cepheid variable as a standard candle if the galaxies are at a distance less than 50 megaparsec. And when he plotted a graph of speed of recession against distance, the distance of these galaxies were measured by using Cepheid variable as a standard candle. So the galaxies, those are less than 50 megaparsec. He got a graph like a speed of recession against distance graph. The best fit line is a straight line through the origin. So it's actually not a perfect straight line. The best fit line is a line which is passing through origin. So the distance is measured by using Cepheid variable as a standard candle. So he would have used the galaxies, those are at a distance less than 50 megaparsec. So from this graph, he said V proportional to speed of recession is directly proportional to distance of the galaxy from us. So speed equal a constant. Later that constant is called Hubble constant H, or some books they call H naught. So the value of H naught is almost equal to 70.9 kilometer per second per megaparsec. So the distance was measured in megaparsec. The speed of recession was measured in kilometer per second. So the Hubble constant is in the unit of 70.9 kilometer per second per megaparsec. The Hubble constant has very large uncertainty because the distance, the measurement of distance has very large uncertainty because it's almost up to the distance of 50 megaparsec, and he used Cepheid variable method. So there is larger uncertainty in the measurement of distance. Because of large uncertainty in the measurement of distance, Hubble constant also has large uncertainty. Okay, so now we can use this graph to find the distance of much far away distance galaxies. Say there's a galaxy which is much far away, more than 50 megaparsec. So in that galaxy, measure the redshift. We call redshift means delta lambda or lambda. Measure it from the absorption spectrum. Measure the shift delta lambda. So from that, find the speed of recession of the galaxy. If you know the speed of recession of the galaxy, you can extrapolate this graph. So from that, you can find the distance of that galaxy which is more than 50 megaparsec. But there will be large uncertainty in that distance because Hubble constant has larger uncertainty. So in the Hubble, in the Doppler effect equation, we call delta lambda over lambda equal delta F over F equal V over C. This ratio, whether delta lambda or lambda or delta F over F or V over C, this ratio is called redshift. Okay, there could be a question like this. A line in the hydrogen spectrum from a laboratory source has a wavelength of 656 nanometers. So that's actual wavelength. So laboratory source, or we can say in our galaxy, there is no relative motion when we consider our galaxy. All stars are related to us. They are at rest because our galaxy is at rest related to us, is it? So or we can say that is wavelength measured from the laboratory. So there is no relative motion in the laboratory. So that is the actual wavelength of that particular line of hydrogen. In the spectrum of light received from distant galaxy X, this line appears at a wavelength of 684 nanometer. Means there is a increase in wavelength. So this is the apparent wavelength. Hubble constant is given. First part, find the speed of recession of X. So we need to use Doppler effect equation. So first part, delta lambda over lambda equal V over C. So delta lambda means the difference between 684 and 656 over actual is the laboratory wavelength. That's the actual wavelength, 656 equal V, the speed of recession, over 3 into 10 to the power 8. So you solve it, you will get the speed. So speed of recession will become 1.28 10 to the power 7 meter per second. So related to us, it's moving away from us at this speed. Second part, we need to find the distance of it. We can find by using Hubble's law. V equal h naught d. So d is going to be V over h naught. So we can find it in megaparsec. Find the distance, we can give it in parsec, megaparsec. V is, we know, 1.28 10 to the power 7 meter per second over h naught is given 70.9 kilometer. So we'll convert to meter because here is meter. So multiply by 1000 meter per second per megaparsec. So megaparsec will go up. Meter per second will get cancelled. So we'll get the final answer in megaparsec. Solve it. So almost 181 megaparsec. Okay, so next thing is about how to estimate the age of the universe from the Big Bang. Okay, so we take two assumptions. First assumption, we take all the galaxies before Big Bang, all the galaxies were together closer to us. First assumption. Second assumption, all the galaxies are moving away from each other at constant speed after the Big Bang. Two assumptions again I'm saying. First assumption, all the galaxies are together closer to us. That means we are the midpoint. The Earth or our solar system or our galaxy is the mid of the universe. We assume like that. Then second assumption, all the galaxies are moving away from us at constant speed after Big Bang. So by using that, we can find the age of the universe. Okay, so imagine we are here and there is a galaxy somewhere here, another galaxy. So the distance it has moved is d, and we assume it's moving at constant speed. So we know that speed equal distance over time. So the time taken by this galaxy to complete this distance is the age of the universe, because we assume all these galaxies were together with us. Now it has gone to this position, a distance d away from us means, if I find the time taken by the galaxy to reach this position, or the time taken by the galaxy to move a distance d from us, is the time duration from the moment of Big Bang. That is the age of the universe. So speed equal distance over time. So time equal distance over speed. But it will a very approximate method. So but I know that v equal h naught d. So time equal d over h naught d. D and d will get cancelled. 1 over h naught, that is the age or the time taken by this galaxy to complete a distance d from the moment it was with us just before Big Bang. So age is given by 1 over h naught. You know the h naught is equal to 70.9 kilometer per second per megaparsec. Okay, we'll find whether we are getting, you can check it in the internet or any books. It says age of the universe is almost 14 billion years. We'll see whether we are going to get the age 14 billion years. We'll find it now. Okay, you should be able to get that expression age equal 1 over h naught. So age equal 1 over h naught. So first I should convert the h naught to simplify it to a normal unit rather than megaparsec. So we'll find out that first h naught is equal to 70.9 kilometer per second per megaparsec. Okay, that means 70.9 kilometer. So 1000 meter per second per megaparsec means megaparsec, is it? Per mega, there's an index -1 means 1 over megaparsec. So convert this 70.9 into 1000 mega 10 to the power 6. 1 pc, that will be given in the question paper whenever they ask this question. 1 pc is equal to, I already derived it. 1 minute. 1 parsec is equal to 3.09 10 to the power 16 meter. So here meter per second. Is it? So 79.9 kilometer into meter per second. Make our parsec. So it's going to be, sorry, I think I made a mistake. 70.9. Okay, I'm fine. That's right. Yeah. Meter per second. Okay, we'll get the answer in per second. Solve it. We'll get the answer h naught in per second. Okay, so that's the value of h naught. So age of the universe equal 1 over h naught. So that is going to be 1 over per second, 2.29. 10 to the power minus 18 per second. So when it goes up, it will become second. So solve this value. That will be 4.36. 10 to the power 17 seconds. Convert to billions of years. So to convert this to 4.36, 10 to the power 17. To convert to minute, divide by 60. To convert to hour, divide by another 60. So second to minute, hour, hour to day, day to years, billion, 10 to the power 9 billion years. Solve it. We'll get in 13.8. That is approximately 14 billion years. They can ask this calculation. Okay, so the next topic is dark matter. So what is dark matter means? It's a composite of particles that do not interact with electromagnetic radiation. Or you can say dark matter is a composite of particles that do not absorb or reflect or emit any electromagnetic radiation, but it can interact gravitational by using gravitational field with other matter. That is the dark matter. Okay, so what is the evidence for dark matter? So you should be able to understand the meaning of dark matter. It's a composite of particle. It does not interact with electromagnetic radiation, or you can say it does not emit or absorb or reflect any electromagnetic radiation, but it has gravitational interaction with other matter. Right, so what's the evidence for dark matter? Okay, so this is the evidence for dark matter. It's like this. When you consider a particular galaxy, most of the galaxies at the center there is a black hole, and most of the stars are spiraling around the nucleus of the galaxy. Nucleus of the galaxy is the center part of the galaxy. When you consider a galaxy, most of the stars in the galaxy are concentrated closer to the nucleus. The other stars are highly spread out in the outer region of the nucleus. So when we consider a galaxy, for example, this is the nucleus of the galaxy, there will be a black hole, and most of the stars are very closer to the center of the galaxy. So we can assume most of the mass of the galaxy is concentrated at the center of the galaxy. We can assume most of the mass of the galaxy is concentrated at the center of the galaxy due to visible matter such as stars. Okay, so we know that in gravitational field you would have learned when a star moves around a galaxy, it moves due to the gravitational force acting on it. The gravitational force acting on it is the F equal g mm over r square. we can say the gravitational force F equal G mm over r squared, and the speed of the star when it orbits the nucleus of the galaxy is given by V equals square root of gm over r, where m is the mass enclosed within the spherical path. You know, the star is moving on a circular path. We can assume a sphere of the radius or the distance r of the star from the center of the galaxy. If I say that distance is r, so m is the mass of the stars enclosed within the sphere which has radius r. It's actually Gauss law, but the word Gauss law is not in your syllabus. So Gauss law says m is the mass enclosed within the region occupied by the motion of the star. So that is the m. Okay, so what observation they made? I told that most of the mass of a galaxy are concentrated closer to the nucleus of the galaxy. So when we consider another star which is far away from the nucleus, and its speed when we consider, so its speed should be given by V equals square root of gm over r here. So you can argue the radius of this star is larger, so it might include more mass, but that's not the case because most of the mass is concentrated near to the nucleus. So there's most of the mass means the mass due to the visible matter stars enclosed within the or closer to the nucleus. So the mass enclosed due to the visible stars within this sphere or within this sphere is almost same. There's no big difference. The mass enclosed within this sphere or this sphere should be almost same because most of the visible stars are concentrated closer to the nucleus or closer to the center of the galaxy. So when we think about this speed v1, where the mass is same as this mass, but the distance r1 is larger, so this star should have lower speed. But when they measured by using satellites, when the scientists measured the speed of a star in a far distance from the nucleus of the galaxy, they found the speed v1 and speed v are almost the same. Their argument, the mass should not have very big difference in terms of visible stars because most of the stars are concentrated closer to the nucleus, but R1 is much larger than R, so V1 should be much smaller than V. But when they measured the V1, they observed V1 is almost equal to V. How is it possible? Then they gave a conclusion. The only possible conclusion we can say here is, okay, the visible mass are concentrated closer to the nucleus of the galaxy, closer to the center of the galaxy. But when we consider this star, this volume is enclosing some other matter that is invisible. There should be some other matter which is invisible exist in this region that gives the additional mass such that V1 and V becomes the same. That mass is due to dark matter. Okay, so that's the only evidence scientists have. But there's one more evidence about gravitational lensing, not in your syllabus, but in your syllabus, this is the only evidence we talk. So this is the evidence we can tell in your syllabus to show the existence of dark matter. Okay, what is dark energy? Okay, so what's the evidence of dark energy? You know, all the galaxies are receding from each other or receding from us, moving away from us. We have the Doppler effect equation. There's a redshift in the absorption line. So they are moving away from us. But even when they are moving away from each other, there must be gravitational pull towards each other. So they should slow down. They experience gravitational force towards each other even when they are expanding. But we know that according to Hubble's law, V equal h naught d, the distance increases, their velocity is increasing. That means when a galaxy is at a particular distance today, maybe after a few years when the galaxy comes to this position, or after millions of years, when the galaxy goes to this position, the speed is increasing. Even when it has gravitational pull towards each other, which is opposite to the motion of expansion. So how is it possible? From where are they getting the energy for acceleration? They are gain in energy, gain in kinetic energy. So it's another puzzle. So this energy increase in velocity is due to unknown energy, which is filling the distance or filling the region between the galaxies. That energy is called dark energy. So dark energy is the energy which is accelerating the galaxies to move away from each other such that their velocity or speed increases. The evidence for increase in speed is the Hubble's law. Okay, that is the dark energy. Okay, it's a very common question students ask. You know, we learned that in unit 4, according to special theory of relativity, mass has equivalent energy, energy has equivalent mass. So dark matter, dark energy, the word dark is the same, but one is matter, the other one is energy. So students normally they ask, is the dark energy is equivalent of the dark matter, or is the dark matter is equivalent of the dark energy? No, they are completely two different things. One is dark matter that exists within the galaxies, that provides gravitational effect, that provides gravitational pull to matter, which has no interaction with electromagnetic radiation. But dark energy exists between the galaxies, which provides the energy for acceleration of the galaxies. So they are two complete different entities. They have no direct relationship. So dark matter and dark energy are not equivalent to each other. They are completely two different entities. Okay, next topic is cosmic microwave background radiation, or short form it's called CMBR. Actually, it was detected accidentally during 1965 when two researchers belonged to Bell Telephone Laboratory. They made a radio receiver and they found it was receiving an unknown noise in the region of microwave, and it had the same intensity all part of the sky, all part of the earth in different time, different locations. There is no difference in the intensity. So later scientists did research about it and they found that according to Big Bang theory, after almost 38,000 years from the Big Bang, the universe consists of dense plasma. Then when it cooled down after 38,000 years, it formed electrons and protons, but they coupled together strongly. But later, when the universe expand and cool down, these protons and electrons, they formed hydrogen atoms. When these hydrogen atoms are formed, this process is called recombination. When these hydrogen atoms are formed from the protons and electrons, energy was released, and that energy was initially at that time high radiation. It was with high energy radiation, with high frequency. But when the universe expands further, the temperature decreased and the radiation now in the region of microwave with a temperature of average temperature of 2.7 Kelvin. So what is the evidence of CMBR? So cosmic microwave background radiation is one of the evidence for Big Bang, in which initially it was high temperature plasma. Because of the Big Bang, the universe is expanding, and when it cools down, the temperature currently, the average temperature becomes 2.7, and the radiation should be in the region of microwave. So the experimentally what they measured is in the region of microwave. According to the Big Bang theory also, it should be in that region, because the Big Bang theory predicts the temperature should be currently almost 2.7 Kelvin. So CMBR, the cosmic microwave background radiation, is one of the evidence for Big Bang. The other evidence is you can say the redshift in the radiation or light from the galaxies is the second evidence for Big Bang.